Yeah. If I could not have that, my life is like that. Yeah. I love my dog. It's like as if they're going to have substance. Yeah.
You smile. Okay, great.
You studied
But it's always instilled. Yeah, when I'm like, so then you can tell I'm not totally good.
And it would be nice to like continue, but actually New Year's would give me like, oh my god, I'm dying, that's crazy.
But.
Go for it. Yeah, I'm the sixth major.
Yeah, I don't think all it's like church they only take like 2 minutes.
We didn't have to where I don't even, like, I'll like. She could be looking at us and see great like conferences, like we've always gone like. The children go to the party, right? So it was cool to be able to do that. She's alive.
My country, I went all the way to college, so like, and I had this church where they combined English, Spanish, and
Yes, I
still managed, yeah, I'm sure.
like first grade.
And I still managed to get my math.
Yeah, that's so wrong because I know you were there. But I like to forget that like I don't it's a little.
Okay, did everyone pick up the test review packets? When you guys came in? So let's try number one. You'll get to use your calculator, which means that you could see the graph in your calculator and we can practice doing that. But we're gonna do everything without a calculator, and then we can confirm our answer with our graph. Okay, so let's read the problem here. Let f be the function given by f of x. Write an equation of a line tangent to the graph at the point 2, -28. So tangent line equation, what information do we need to build a tangent line equation? We already have the ordered pair. We just have to find a way. Slope, yeah, slope from f prime. So try that. So f prime, we go through power rule. And then once we have our slope formula, our derivative function, we can insert the x value 2 in to get our slope. Our slope is 24. We have our order pair. We have our slope, point slope form. Okay, it says find the absolute minimum. Let's just do this. Let's just find the relative minimums. And then from the relative minimums, we can compare the two y values to see which one is lower. So let's go through first derivative test. Find f prime, find your critical points, create your slope sine line, and determine where your relative minimum are. From f prime, we can set equal to 0, factor out GCF, continue factoring. We'll get 0, -2, and 7/4 as our critical points. Put them onto our sine line, test each subinterval, and we can have an idea how our graph is rising and falling. And we see two relative minimums, so we can test to see which one is lower between these two. So anytime I'm looking for an order pair, I can involve the original function, plug -2 and 7/4 back into the original function, and see which one produces the lower y value. And we know that one of these will have to be the absolute minimum because of the way that the graph is shaped, right? This is a degree 4 function, and our degree 4 is going to have arrows on both ends. So one of these two relative minimums will have to be the lowest points because we know the graph is not going to come back down and head towards negative infinity. So f of -2 gave us -44. F of 7/4 gave us -30.816. We have the lowest y value being -44, so absolute minimum value is -44. Okay, part C, find the x coordinate of each point of inflection. To get to the point of inflection, we have to make our way down to which derivative level. Point of inflection, is that coming from the original function, from f prime or f double prime? There. How do we get to point of inflection information? Second derivative, right? Second derivative. Okay, so let's make our way down to f double prime. We set f double prime equal to 0, factor our second derivative of the function, and factor out 6. Continue, once you take out GCF, continue factoring. Gotta pack it. We can test negative 2, we can test 0, we can test 2. And gather the signs for each subinterval. Positive would mean concave up, negative would mean concave down. Because there's a change in signs, we see point of inflection at both those critical points. If you have your graphing calculator, you can confirm all this. So if you go to y equals, top left-hand corner of your graphing calculator, you can type in your function, your original function. And it should resemble the x to the fourth graph that we see here. -2 is going to produce the lower y value. 7/4 will produce a higher y value. We expect the graph to change from concave up to concave down, back to concave up. So under y1, you can type this in, 3x to the fourth plus x squared minus 21, sorry, plus x cubed minus 21x squared. I like to do zoom 6 as a way to kind of get my graph to show me something. If I do a standard window, that just means it's going to stretch as far left as -10, as x equals -10, as far right as +10, as far down as -10. So if you do standard, it's basically going to give you a window where your furthest x value is -10 to +10, the y value is from 8 to 10. Sometimes the graph doesn't quite show you everything. As you can see, if you hit graph, 6. And get an idea that it's trying to show us that fourth degree polynomial, but it's not going down far enough. But we know where our y value is. Our y value is all the way down to the -40, -30. And if you go to window, you can see your x min, x max, y min, y max. These are the x and y values that are as part of the standard window. And we just have to kind of push that y min to show us a little bit more. So we can push it all the way down to, I mean, we can go to -44, or we can get down to, I would say, -50, just so we can kind of see around the edges a little bit. Anytime you want to adjust your window, you only have to play with those 4 numbers: y min, y max, x min, x max. The other numbers, you don't have to. Yeah, it doesn't help to change those numbers. So if I hit graph again, I should be able to get a picture of my polynomial. All right, let's go to next page. Actually, I'll save number 2 for tomorrow since it's a similar process. We're just building first derivative test, second test for concavity. Let's go to page 3 and let's look at interpreting a derivative graph, an F prime graph. Remember the chart that I shared with you? Sometimes that can come in handy. This really helps if you're looking at the F prime graph. If you're looking at the F prime graph, you know your x-intercept is going to match up with the max and mins of your original function. The max and mins of your F prime is going to tell you where the original point of where the point of inflection of your original function is. So it really comes in handy at this level here. So your point of inflection on the original graph will look like a max and min on your F prime, which will look like an x-intercept on your F double prime. All right, so let's see. Determine the values where our graph of G has a relative minimum and relative max. So keep in mind, this is the F prime graph. This is not the original graph, so we can't quite as easily say, okay, there's my relative max, there's my relative min, there's my relative max. Easy enough. If this was f of x, that'll be easy enough. But this is F prime. We're asking about the behavior of the original function, which we don't see in front of us. We have F prime in front of us. So we can help remind ourselves that our y-axis represents not the y value of the original function. These represent the slope values of the original function. So we can kind of label our graph accordingly to help remind us that anything above the x-axis is where the original graph is going to be experiencing a positive slope. Below the x-axis, our f of x is experiencing a negative slope. On the x-axis, my original graph is experiencing a slope 0. So where do we find our critical points for our f prime sign line? We want to do that first here. They tell us to go from -3 to 4, so we can build out our sign line from -3 to 4. Okay, where do you see our critical points that we can put onto our f prime sign line? Do we want to say -1, 1, and 3, or something else? Right, we should go after the what? Yeah, x-intercepts, right? X-intercepts will translate to a max and min on the original function. So what can we say as our x-intercepts? Where else? 0 and 2. Okay. All right. Don't look at the rise and fall of the graphs. Look to see if the graph is above or below the x-axis, and you're going to use these as your indicators to tell you what's happening with the slope. So between -3 and -2.5, what's happening with my original graph? Rising or falling? Falling. Yeah, it looks like it's rising on the f prime side, but these are all different variations of negative slope. So we want to follow where the graph is located. It's below the x-axis, so you start off negative slope. Okay. Between -2.5 and 0, it's going to switch over to being above the x-axis. So we want that to be a positive slope. Between 0 and 2, below the x-axis, and then between 2 and 4 above the x-axis. So this is how the actual graph is going to look. It's going to fall, relative minimum, rise, relative max, fall to some min at 2, and rise again. We can answer part A and B after we sketch our graph. I just want to be able to get to our graph because determining relative min, relative max, that's pretty straightforward. You just look at the arrows and you just have to make sure you can continue to write your because statements. Let's see if we can build our second derivative sign line. Again, the endpoints are provided, -3 to 4. So where do we look if we're trying to find the points of inflection off of the f prime graph? Look at the what on the f prime? What does that m stand for? M represents what? Yeah, max and mins, right? So your max and mins on your f prime is going to tell you where the points of inflection of the original function is going to live. Right. So -1, 1, and 3. So on the f double prime sign line, we want to gather information about our concavity. Now, this is not the original function, so we can't say, oh, this is concave down, this looks concave up, this looks concave down. We have to look at it a different perspective here. We have to look at the slope. So if the slope of f prime is rising, what does that mean? That means my original function is going to look like what? Concave. Positive slope on my f prime means what concavity on my original function? Positive slope means concave, what? Up or down? Up, yeah. So positive slope is concave up. Negative slope means my slope is becoming more negative. If the slope is becoming more negative, it's going to end up looking like upside down U shape. Imagine slope of 3, then 2, then 1, then -1, then 0. That's going to end up shaping like this. Okay? Positive slope on the f prime, back to concave up. Negative slope on the f prime is concave down. All right. Now, based off of this, we're going to see if we can sketch our f of x graph. They do give us some information for us to plot. We know we have some anchor points on the f of x, so -3, 3, and 4, 6. Let's go ahead and plot those points. So we know our graph is going to start here and here, and we're going to try to just get our slope to show up. We're going to just follow whatever the arrows are doing, and I'm going to purposely cover up my f prime because I know this is not going to be of any help. If we look at f prime, we're going to start copying f prime, and we know our f of x looks nothing like our f prime, right? Because the y-axis is defining something different. So starting here, we know we want to fall to some relative minimum at -2.5. So I'm just going to target some relative minimum for me to go after here. So I want my graph to fall. You can have it lower, you can have it higher, it doesn't matter. We just know that we're expecting a relative minimum at -2.5 somewhere. And then at 0, I'm going to target a point higher. So I can move towards that relative max. And then at 2, I'm expecting a relative minimum. Doesn't matter. I could have it lower or higher than my other relative minimum. We really don't have enough information. right now. And it doesn't really matter. Right now, we just want to get if we can just get the basic path of the graph, we can go back and do the concavity of it later. So fall to some relative minimum at negative 2.5, rises up to some relative max at 0, falls again to some relative min at 2, and rises again to 4. So along the path of the graph, your graph may be higher or lower than mine, but we should all have a similar rise and fall of our graph. At -1, wherever your graph lands at -1, go ahead and highlight that point. So mine is somewhere up here. At +1, wherever your graph lands at x equals 1, highlight that point. And then at 3, highlight that point. Okay, so now you're going to go back and retrace your graph with the proper concavity, curvature, concave up, followed by concave down, back to concave up, and then concave down. And then finally, I want you guys to practice writing out your because statements. I gave back your quizzes. I think some of us are still having trouble writing out our because statements. Some of us are writing because the sign changes or because it changes. We want to make sure we specify what's changing, right? So you got to say either f prime is changing signs or f double prime is changing signs. Relative max, relative min, they both have because statements. And so does point of inflection. It doesn't specify point of inflection, but let's go ahead and write out that statement as well. So if you can write out your statements of relative min, relative max, concave up, concave down, and points of inflection. Okay. Relative minimum at x equals -2.5 and x equals 2 because G prime changes signs from negative to positive. Relative maximum at x equals 0 because G prime changes from positive to negative. Concave up in these two subintervals because G double prime is greater than 0. Concave down at these two subintervals because G double prime is less than 0. Point of inflection at -1, 1, and 3 because G double prime changed signs. Okay, I just want to know what our comfort level is with this type of problem. And so I want us to try page 7. Um, if you can you can do your slope sign line, concavity sign line, and do a picture of your graph. I know that you guys are good. And we can, otherwise, I would like to know where our trouble spots are so I can address it. But if you can go to page 7, try it. It's the exact same process as this. It's asking for a bunch of information, but I just want you to create your slope sign line, create your concavity sign line, and then build your graph in 2 stages, right? First stage, just following the path of your arrows, and then you can go back and give it the curvature around your points of inflection. Okay, so try that. I'll walk around, see if I can help you. You guys can also check your progress with the key. Whenever you create your second derivative sign line, if I'm looking for points of inflections, right? Points of inflection is going to live as the max and mins of your f prime graph. The slope of your f prime is going to translate to the concavity of your f double prime. So negative slope is going to translate to concave down in your f double on your as far as concavity goes. Okay, we should be able to sketch our f of x graph at this stage. Again, I think it's really helpful if you can somehow cover up your f prime so you're not looking at your f prime graph. If you try to look at the f prime graph, try to sketch your f of x, you're going to copy the graph, and that's not what we want, right? These should look very different from each other. Okay, we do have some anchor points here, -5, -4, and 5, 3. All right, I just want to follow the path of my graph, of my arrows here. I want my graph to rise. Anytime there's a tick mark, I'm expecting a slope 0. So I do need to have the graph flattened out for a moment. It's not going to be a relative max, relative min, because the graph is going to rise, but it's going to rise, level off, and continue rising. So I do want to have some target at -3 where my graph can kind of flatten out for a moment. Continue rising until it hits a relative max at -1, which is going to pick a random point that's high. And it's going to go to some relative min at 3. I'll pick a point. And now I'm just following the path of my arrows. I'm not committing to the curvature of the graph yet. I just want to get the path down. This is purely based off of my slope sine line. Okay. And really just whatever the arrows are telling you, that's what you're going to do, right? You follow whatever the arrows are telling you. And ish, I think it's really helpful looking at the arrows to help guide your path. Now, there's one other thing that I haven't talked about before we get to the curvature, and it's the range. It says the range is from -7 to 5. What does that mean? The range is what values? What's the range referring to? The y values, right? So that means wherever my graph looks like, I just need my lowest y value to show -7 and my highest y value to show 5. So which point can I drag to make it go down to -7? This point, right? This relative min. I can't drag the endpoints because the endpoints are set, but I can drag this down to -7. So, or if you just want to reassign your y values, and wherever it lands, you just give it that y value that it needs. And then I just need to go as high as 5. So I'm just going to rearrange my tick marks to show -7 and 5. All right, so now I'm going back and identifying all my points of inflection. So -3. Again, these are not going to be new points on the graph. You're just going to, wherever the graph falls, just highlight that point. So wherever the graph lands at -3, wherever the graph lands at -2, wherever the graph lands at 1, and then 4. And then from dot to dot, you're just giving the proper curvature within each interval. Concave down, followed by concave up, then concave down, then concave up, then concave down. Okay, one more thing is let's sketch our f double prime graph. F double prime graph is purely based off of your f double prime sign line. And looking at your chart, you know that your points of inflection is going to land on the x-intercepts, or it's going to show up as x-intercepts. Right? So your point of inflection will land on the x-axis if it's f double prime. Above is concave up, below is concave down. And your f double prime graph should look the simplest out of the three. Okay, so it should have the least number of curves. So just keep that in mind. So we have our critical points, -3, -2, 1, and 4. And you're just threading between these points. And we're going to be told where to start. We're going to start below the x-axis. And we're going to go above, then below, then above, then below. And we're just going to go through those points. And the shape of the graph will look nothing like the shape here. Okay, so understand that this shape is for the original function. All we're doing is we're using this to indicate where we're going to land, either above or below the x-axis. But you're not going to try to shape the graph to look like these. Okay, let's finish off by writing out all the because statements: relative minimum, relative maximum, interval increase, interval decrease, point of inflection, concave up, concave down. I know that you guys can identify all the points, but can you write the because statements that's associated with each? Okay, your homework is just going to be page 8. Page 8 is a more of a straightforward problem where you're given the original function, you build f prime sign line, you build f double prime sign line, you gather all that information, And the key is on page 10. So I'll send out a reminder. Your homework is just page 8. All right, can get your phones. You're doing the. Yeah. I would do parentheses. I probably won't take out points for practice, but I prefer parentheses.
I don't know if I'm- I don't know what I'm gonna write down.
You got it. Only on the graph thing. Like, I haven't got anything. And I don't know.
The lab is like.
Oh, yeah.
That's the last time I keep that, so they might have lost like I said. Me too.
Thursday, Friday.
Yeah.
It's like, I don't have, so it's not.
You have.